I have this Angry Bird stuffed animal. I'm going to throw it through the air. What I'd like you to do, take a minute, sketch a free body diagram for the bird while it was in the air. It's a little bit wild, but the entire time that object is in the air, there's only one force on it, and that's gravity, which is what we know as a vertical or y-axis force. People want to think the throw has something to do with it, but once you let go, you can't put a force on an object anymore. So as it's flying through the air, if you can ignore drag, we just have a vertical force. Let's take a look at a motion that is purely vertical, just to kind of refresh ourselves to what that looks like. We understand the motion really well if I throw this Angry Bird straight up and down. Let's plug a video of that into Tracker and look what kind of position time graph it gets us. That's what we'd expect when we look at the free body diagram. Our upward vertical velocity is going to be opposed by the downward gravitational force, so we'll get slowing. Our downward vertical velocity is going to be in the same direction as it, so we get speeding up. So this is kind of a review of what we've already done. What would happen, though, if I threw the bird at an angle? In other words, my original velocity was represented by this orange VO. That's not up, it's up and right. And we could almost think of it as being two separate motions. Part of that throw will be making the bird move right, and part of it will be making it move up. Let's take a look at what that looks like. I'm going to throw it at an angle now. I'm going to give it a diagonal original velocity. Let's plug that into Tracker and see what we see. So here's what that looks like after you plug it into Tracker. And here's our graphs of motion. Notice one of them says time, comma, x. That corresponds to the left-right motion of the bird, which in this case would be in this direction. It's basically going to ignore any up-down motion. We have to do this because there's only room on a graph for two variables, and we give one axis to time. So this graph tells us what's happening about the bird as it moves left and right. This one tells us about the bird as it moves up and down, which in this case is essentially rising at first and then falling down. I think looking at the vertical motion is probably the most interesting at first. Notice that it's exactly the same as what we saw before. It's a parabola. And just like before, it's our usual constant acceleration equation. That makes sense because in the vertical dimension, we still have that force of gravity. So we expect gravity to slow the thing down as it goes up and speed it up as it comes back down. That's exactly what we see here. But check out this. Horizontally, we have a straight line. As time passes, we always increase the same amount of distance in any given time period. That's the hallmark of a constant velocity. So it's almost like our horizontal motion isn't affected by any force at all. Why would that be? Well, if we go back to that idea of breaking diagonal motion into pieces, we can see that the vertical piece is in the same dimension, the y-axis, as gravity. And we know what it'll do. Gravity will slow this velocity down because they're opposed, and it will speed this velocity up because they're in the same direction. But what about this right piece? That's not in the same dimension as gravity. It's not clear how gravity would have any effect at all. And at least according to our graphs here, it seems that left-right, gravity's having no effect. It's almost like there's no force at all. I have sort of a silly way of remembering that idea that horizontal and vertical seem to be separate. There's an old tourism slogan for Las Vegas, what happens in Vegas stays in Vegas. It sort of applies to what we're seeing here. We saw that the vertical force of gravity only seemed to affect vertical motion. What happens if vertical stays in vertical? We're going to see that it's also true that what happens in horizontal stays in horizontal. Horizontal forces only affect horizontal motion. We can deal with diagonal motion by taking things that are up and to the right and breaking them into pieces. How much is this to the right? It's kind of the shadow that that purple arrow casts on the ground. How much of this is up? It's kind of the shadow that purple arrow casts on a wall. So that's what we'll be doing in this unit. We'll be solving basically two separate problems. One in the x dimension, one in the y. The equations we'll use to solve our two-dimensional motion problems ought to look familiar. It's just two copies of our constant acceleration equations. If you look closely, there's a bunch of little subscripts added on, and that's because of this big idea that left-right motion and up-down motion don't affect each other. So every problem will essentially be two problems, and we'll have to be very sure we're putting the right numbers either into horizontal or vertical, but the process ought to be pretty familiar. If you're feeling unclear about how we break motion into two pieces, hopefully this picture will help. We've said that horizontally, that throw appeared to be constant velocity. Our graph tells us that, and the fact we have no horizontal forces tells us that too. Remember, this red track is what my Angry Bird actually did. If I ignore the up-down motion and just draw a circle at the same left-right distance for a bunch of these, we see that those circles are evenly spaced. That's what we'd expect for something moving at constant velocity. If we ignore the left-rightness, we see that they start to spread out more and more and more. That's what we'd expect for constant acceleration. So this is what it means to break something down into pieces. We're going to look at just this motion. And then we're going to look at just this motion. And we're going to see what links the two. The key idea is that horizontal and vertical are separate. I want to hit pause here. I'd like you to take a look at a clip from an older video from PSSC Physics by Professor Nathan Frank of MIT. He does a really good job showing this separateness. In the problem you've seen so far, I threw the Angry Bird at an angle. It had both horizontal and vertical motion to begin with. We're going to ease you into these kind of problems a little bit easier. We're going to look at objects that are moving purely horizontally, and then they fall off a table or a cliff or something. So in other words, they don't have vertical motion to begin with. They purely have horizontal. In the next video, you're going to see me working through a version of that problem based on an old lab I used to do. And then we'll talk about how we can set up a lab ourselves and collect some data on this ourselves.